do, I learned how to erase you. I've been lost in time, forgetting my mind. If I knew what to do, I learned how to erase you. If I knew what to do, I learned how to erase you. If I knew what to do, I learned how to erase you.
All right. Starting on chapter 12 this morning, which is system and process information. This is proc and a bunch of other stuff being covered here. So in this chapter, we look at ways of accessing a variety of system and process information. The primary focus of this chapter is a discussion of the proc file system. We also describe the uname system call. I didn't realize the system call, which is used to retrieve various system identifiers. Let's see. If we use strace on dash C uname dash A. So it ran a bunch of stuff here. One of them was uname here. So man to uname. So you hand it a struct, and it gives you back a error code probably. Uname returns system information in the structure pointed to by buff. The UTS name struct is defined in sys UTS name. So sysname, node name, release, version, machine, domain name. The length of the arrays in a struct UTS name is unspecified. Cool. So basically a bunch of char stars. Okay, just as a test here, mkdir chapter 12 rsync. That's a chapter 12. Sorry. Okay, and here, build them clangs needs to be chapter 12 here. Excuse me. I woke up this morning, I was just completely like feeling like garbage. I have like congestion and stuffy face, so I might just call it quits early today, but I wanted to get a couple hours in on this book, so I think everything should be good here. Let's open up a C file here, just call it uname.c. Give us our main, main. And here, return, exit, success, sure. I just want to call this syscall uname, and oops. It's kind of hard to type with this book in front of you. So uname, gonna say I want a, let's see, sys uts name.h, and then here we gotta declare that we want a struct uts name buff, and then can I like zero it out like this? doesn't look like I can do that. But if I go to definition on this thing, whatever. I don't need to zero it out. UTS name, I'm gonna point to it, buff, and that gives me back the returns. I say if that is less than 0, then we had an error. Maybe we could just p error and give it like uname and return exit failure. P error, I think it's errors or error now. .h, no, errors, error.h. Let's try that. Nope. Let's do man p error studio standard IO. Okay. Cool. All right. Jump to chapter 12. Make build. Oops, got an error. No. Build. You know. I need to print out the buffer now. So here, say printf out with a new line. We'll give it each of the fields here of buff, which there is a few. So here I'm gonna say buff. It's not a pointer, it's local on the stack. Let's say sysname. We'll do sysname $s like that. Node name. And then release. Version. And machine. Oops. Machine. And I'll just do a print and give it uname result. And then I'll just space these in. And then what else we got here? We got machine, and then it says if UTS name domain length -1 or -0, use the domain of this node network. If def, use GNU domain name, else char domain name. Well, try a domain name here. Okay, it's not liking that, but GCC likes it, so we'll run with it. Do I need a flush? I don't think so. There we go. Okay, so GCC doesn't like it. So can we do under domain name like that? There we go. Why does that not run? Go. Oops. Yeah. We should be hitting these. Oh, there's a return exit success right here. I don't know why I skipped over that. Okay. There we go. And if I do uname -a, it's Linux, node name, and then this is the release, then this is the version. And then this is the machine, and this is the, wait a minute, where did that come from? So that's the operating system. Where does it get that from? Sysname, but that was Linux. Where does it get that GNU stuff from? Oh, interesting. Like the Linux kernel is saying, "Hey, I'm Linux," but then, of course, when you do uname -a, because it's probably like a GNU utility, that's why they add the GNU to it. I bet you it's some bullshit because it's a GNU uname. So man uname. And if we go down to the bottom here, yeah, GNU software core utils uname. If we look at O operating system, I'd like to see the source code for this. GNU core utils source. Alright, I'm going with the git. And then maybe just hit up uname here, uname.c maybe. Yeah. And if we look at -o maybe, yeah, operating system. Operating system, no argument, null pointer O. O gives you print operating system, and then okay, host print element host operating system. Okay, if we look at print element, f puts element. What is this thing? Host operating system. Where is that defined at? Huh. Why is this like not defined? It's GNU. That's all licensing stuff. Okay. Sys UTS name maybe? config.h. Let's hit up sysutsname.h. utsname.h. No. Config.h. Nope. Is this a Linux thing? A Linux header? Let's find out. Find on root, type file, name is utsname.h, redirect standard error to dev null. Yeah, looks like it's a Linux thing. Nope. Let's go under user include and then rip grep for this host operating. I don't even see it there. Where are these guys pulling this? Maybe it's in the compile step of it? I don't know. Let's search this repo. Huh. It's very confusing. I'm going to go to source, GitHub, and I'm just going to clone this thing down. And I have to mkdir core utils mv. Oops. I don't care. Core utils doesn't matter. It's an org with a single repo, right? No, they got other stuff. Damn it. Okay, so I have to go back here. mv core utils do core utils 2, mkdir core utils, mv core utils 2, and do core utils cv in there, mv core utils 2 to core utils e. There we go. Now we're in the right directory. Cool. Rip grep for this. Oh, not that. I want to know where this host operating system is. The thing is to find out. That's the only place it's to find it? This print element is defined here, and it's a char star. Yeah. Where is this defined at? It has to be in the build system somewhere. They call it a kernel name here. So if we look at where print kernel name is, here's a syscall right here. Reads it into name. And then there's a printed out, yeah. Let's ask AI. In uname.c, in core utils, there is a char star called that I can't find the definition for. Where would it be located? Autoconf at build time. Oh, so that's what that config.h is. Okay. Yep. Yep. Do I have a configure script here? There's a configure AC. Find iname config.h. No. Configure. No. There's no configure script here. There's a configure AC. No. Can I find... Nope. Of course, this freaking file is huge. AC config headers. Okay, so maybe we go to was it user include and try to find from here that config.h. Okay, there's a lot of them. Oh wow, lots of, I guess that's all the autoconf projects. Is there one just in the root? No. Lib? No. Let's just look for config.h without any of these wildcards. Yeah, okay. HN. No. Bootstrap, okay. Bootstrap. Gperf not found. Oh, so annoying. What does -e do? Okay. Man cc, man gcc, -e. Stop after pre-processing stage. Do not run the compiler program. The output is in the form of preprocessed source. Okay. Well, let's try to get into Bootstrap. Readme prereqs. I tried Bootstrap, but it needs prereqs. How do I install all? Alright, let's run our Bootstrap. The fuck is going on here? Go away, please. Yes, go away. So that's strange. this is another example of where the build target. It's so weird. The build target, or the build environment has to be the same as the target environment that it runs. Because like when you run the uname command, it's it's asking the kernel, it's asking the environment that it's running in, hey, what are these values? But when the OS thing is set in the preprocessor as part of a build step, then like if I took this binary and I moved it over to a machine that was not GNU Linux but still had the same syscall table for uname and all the other stuff that it needs, it would run it. It would say, "Hey, I'm GNU Linux," when it's not. So it's just like, it's an odd thing that they would add that. I wonder if it's part of a standard. I don't know. I like the stuff that's just like thin wrappers around the Linux syscalls instead of like, let's put all of our politics into these tools and say it's GNU Linux. And it's like, okay. I mean, obviously they did all the work to implement all this stuff, so they deserve credit for that, for no doubt. But it's just so silly that they would do that. It's very like politically motivated. GNU. All right. Done playing around there. The proc file system. In older Unix implementations, there was typically no easy way to introspectively analyze or change attributes of the kernel. I wonder if there's like, I heard of this effort of them wanting to rewrite a lot of user space tools in Rust. And I wonder if there's like all the core utils stuff. I wonder if, let me ask AI. Get out of here. Is there any effort to rewrite GNU core utils such as uname? Yeah, this utils, core utils, GNU compatible rewrite. Let's check that out. Let's see if they have a uname. Uname. Looks like they do. Uname RS, main RS. Let's check out uname RS. So they have their operating system as OS. Oops. OS. Uname OS 2 owned. What's uname? Uname was defined, or is it imported? Platform new. Where's platform defined at? Can I just click go to definition here? I want to go to definition. Let's move this over here for now. Platform info. Where's this thing coming from? Is it a crate? Yeah, it's a crate called platform info. Where is it on GitHub here? There is source. Is it under the source tree here? Under source? I know they can have like sub crates or whatever. Is there like a platform info in here? Let's see. Platform. Okay, so they have a platform info crate as a dependency. This is the crate, but it doesn't say where its source code's located at. Is that part of the Rust standard library? Let's see. GitHub Rust. And then see if there's a platform info. Crate? No. UUtils core util package. Bummer. Maybe it's under utils here. Platform info. Okay. That was so confusing. Alright, this is the symbol I'm looking for, OS name. Why did, oh, because I did a go to file. It's the search. At least this looks like it's compatible with other targets like Windows. This is reaching for OS stir. So if we look up OS stir, oh, it's the type. It's just a trait definition. Okay, that's the Rust OS stir, not the operating system name stir. Okay. Let's just look at Unix here. Self OS name. Go away, please. Lib What is this libimple thing? This stuff is insanely confusing. Okay, it's declaring mod libimple, and then there's lib. Okay, found it. And then in here, if I duplicate this, go back over to here, main, platform info. Here's source, platform, Unix. There was libimple host OS name. So it's using the config macro, which is probably like a build system thing. See, this is their stupid crap here. It's like the operating system is Linux, but they say, hey, if the target environment is GNU or the target environment is not set, then we're going to say it's GNU Linux. Else, if not, any of these. So if you set the target env to anything other than GNU or empty string, then it'll say, yeah, I'm Linux. I'm not GNU Linux. It just sounds like silly. All the other operating systems are target OS is equal to that, target OS equal to that. Every single one, except for Linux, because of these freaking nut jobs. Anyways, I shouldn't call them nut jobs. Very opinionated people. Alright. Target vendor, Apple, Darwin, yeah. This is the only different one. This is vendor. Anyways, I've looked into this a little too deeply. Let's go back here. Okay. In older Unix implementations, there was typically no easy way to introspectively analyze or change attributes of the kernel to answer questions such as the following. How many processes are running on the system and who owns them? What files does a process have open? What files are currently locked? And which processes hold the locks? What sockets are being used on the system? Some older Unix implementations solved this problem by allowing privileged programs to delve into data structures in kernel memory. Some older Unix implementations solved this problem by allowing privileged programs to delve into data structures in kernel memory. However, this approach suffered various problems. In particular, it required specialized knowledge of the kernel data structures. And structures might change from one kernel version to the next, requiring programs that depend on them to be rewritten. In order to provide easier access to kernel information, many modern Unix implementations provide a proc virtual file system. The file system resides under the proc directory and contains various files that expose kernel information, allowing processes to conveniently read that information and change it in some cases using normal I/O system calls. The proc file system is said to be virtual because the files in subdirectories that it contains don't reside on disk. Instead, the kernel creates them on the fly as processes access them. In this section, we present an overview of the proc file system. In later chapters, we describe specific proc files as they relate to the topics of each chapter. Although many Unix implementations provide a proc file system, SUSV3 doesn't specify this file system. The details described in this book are Linux specific. Obtaining information about a process, procpid. For each process on the system, the kernel provides a corresponding directory named procpid, where PID is the ID of the process. Within the directory, the various files and subdirectories containing information about the process. For example, we can obtain information about the init process, which always has the process ID 1, by looking at files under the directory proc1. Among the files in each procpid directory is one named status, which provides a range of information about the process. We looked at that earlier. The above output is taken from kernel 2632 as indicated by since comments accompanying the file output. As indicated by the since comments accompany the file output. Since. The format of this file has evolved over time with new fields added and in a few cases removed in various kernel versions. Aside from the Linux 2.6 changes noted above, Linux 2.4 added the TGID, tracer PID, FD size, and threads fields. And the fact that the contents of the file have changed over time raises a general point about the use of proc files. When these files consist of multiple entries, we should parse them defensively. In this case, looking for a match on a line containing a particular string, e.g. ppid, rather than processing the file by logical line number. Table 2.1 lists some of the other files found in each prod PID directory. Okay. Selected files in each proc PID directory command line. The command line arguments delimited by 0. CWD, symbolic link to the current working directory. Environ, environment name, list name value pairs, delimited by /0. Exec, symbolic link to the file being executed. FD, directory containing symbolic links to files opened by this process. Maps, memory mappings. Mem, process virtual memory, must lseek to valid offset before I/O. Mounts, mount points for this process. Root, symbolic link to root directory. Status, various information, e.g. process IDs, credentials, memory usage signals. Task, contains one subdirectory for each thread in process. The procpid FD directory. The procpid FD directory contains one symbolic link for each file descriptor that the process has opened. Each of these symbolic links has a name that matches the descriptor number. For example, proc 1968 FD1 is a symbolic link to the standard output of process 1968, referred to section 511 for further information. As convenience, any process can access its own procpid directory under the symbolic link proc self. Threads, the procpid task directory. In Linux 2.4 added the notion of thread groups to properly support the POSIX threading model. Since some attributes are distinct for the threads in a thread group, Linux 2.4 added a task subdirectory under the procpid directory. For each thread in the process, the kernel provides a subdirectory named procpid tasks TID. I'm curious if a single threaded process like my shell, if I do lsla, or I'm just going to cd into proc self task, and list in here. Yeah, there's a thread here. Cool. Where TID is the thread ID of the thread, this is the same number that would be returned by a call to get TID in the thread. Under each proc PID task TID subdirectory is a set of files and directories exactly like those that are found under proc PID. Since threads share many attributes, much of the information in these files is the same for each of the threads in the process. However, where it makes sense, these files show distinct information for each thread. For example, the proc PID task TID status files for the thread group state PID, sig PND, blah, 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 are some of the fields that may be distinct for each thread. System information under proc, various files and subdirectories under /proc provide access to system-wide information. A few of these are shown in figure 12.1. Many of the files shown in figure 12.1 are described elsewhere in the book. Table 12.2 summarizes the general purpose of the proc subdirectories shown in 12.1. Purpose of the proc subdirectories, you got proc. So the virtual file system I'm familiar with are proc, sys, and C groups. So if you look at mount, I have a grep for C group. So sys fs C group. If I grep for proc, oops. There's proc, and then there's some stuff under it for sysfs, bin format miss. And then if I look for just sys, proc sys, there's the sysfs, which has a bunch of stuff under it. I wonder if they talk about sysfs at all. Proc sys fs. Sysfs purpose: expose the kernel object model, devices, drivers, buses, classes, attributes. Backed by sysfs, reflects the kernel's internal data structures, k-objects, primarily about hardware and drivers, not process state files mapped to attributes of kernel objects. Strongly hierarchical and structured, typical contents. They don't mention C groups. Is it under proc CPU info? Yeah. Okay. Proc sysctl interface. Purpose: runtime kernel tuning parameters. Backed by procfs, exposes kernel variables, not kernel objects. Historically older than sysfs, flattish key value tree, mostly mirrors sysctl. Okay. Let's see, proc, various system information, proc net, status information about networking and sockets, proc sysfs, settings related to file systems, proc syskernel, various general kernel settings, process net, networking and socket settings, proc sysvm, memory management settings, proc sysv IPC, information about system v IPC objects, accessing proc files. Files under proc are often accessed using shell scripts. Most proc files that contain multiple values can be easily parsed with a scripting language such as Python or Perl. For example, we can modify and view the contents of a proc file using shell commands as follows: echo 1,000,000 to proc sys kernel pidmax cat out. Proc files can also be accessed from programs using normal file IO system calls. Some restrictions apply when accessing these files. Some proc files are read-only, that is, they exist only to display kernel information and can't be used to modify that information. This applies to most files under the proc pid directories. Some proc files can be read only by the file owner or by a privileged process. For example, all files under proc pid are owned by the user who owns the corresponding process, and on some of these files, e.g. proc pid environ, read permission is granted only to the file owner. Other than files in the proc pid subdirectories, most files under proc are owned by root, and the files that are modifiable can be modified only by root. Cool. Alright, I'm going to take a real quick break here and I'll be right back in a minute.
If I knew what to do, I'd learn how to embrace you. If you could see, if you could just relax.
They didn't have CPU info added to here. Accessing files in procpid. I got myself a tasty beverage here, some matcha. Okay. The procpid directories are volatile. Each of these directories comes into existence when a process with the corresponding process ID is created and disappears when the process terminates. This means that if we determine that a particular procpid directory exists, then we need to cleanly handle the possibility that the process has terminated and the corresponding procpid directory has been deleted by the time we try to open a file in that directory. Make sense? Example program listing 12.1 demonstrates how to read and modify a proc file. The program reads and displays the contents of procsys kernel pid max. If a command line argument is supplied, the program updates the file using that value. This file, which is new in Linux 2.6, specifies an upper limit for process IDs. Here's an example of the use of this program. Okay, just read over this program real fast. Max line is 100. Wait a minute, it's defining max line as 100. Didn't it just tell us not to do that? Oh, let's read through it. We declare a file descriptor and a character array that's 100 in width called line. Then we open up the pidmax with the open syscall. If argc is greater than 1, then we make it read write, otherwise we make it read only. Handle the error, then we do the read into the buffer with and then we print out the old value, which would be n. And then we lseek to 0, and then we write argv1, string length of argv1, I'm curious when you do the write, if the null terminator, like what if you had extra bytes, like say it was 1,000,000 and you set it to 10, would a null byte be inserted to set it to 10, or at the end of the 10 to truncate it, or would it be truncated regardless? Let's ask AI. When using the syscall write to, let's say, slash proc sys kernel pid max to write a new value, do you first need to truncate the file, or can you just lseek to the start and write the ASCII characters for the new value? Do you need a 0 byte at the end to drop the remaining bytes if the old value had more than the current. Okay. Cool. System identification uname. The uname system call returns a range of identifying information about the host system on which the application is running in the structure pointed to by UTS buff. One thing I did want to do is anything that I write in C now, I want to write it in Zig as well. So, because I want to start learning Zig, lang. And then here, I'm just say uname.zig. And don't want to write tests. I just want like a super basic example. Let's just ask AI because this is going to take forever to go through their docs. Give me a super basic example of a Zig program that makes the uname syscall and outputs the result. Then show me how to build and run that program, preferably with a make file target. At some point I want to go through and learn Zig, like legit learn it. I can't believe there's no like super basic example stuff. Getting started. Here you go. Installing Zig. Do I have Zig already? Let's see. Zig? No. Pacman search for Zig. And then I can do sudo pacman.zig. I think I messed that up. There we go. So use Clang, LVM. I think they're like working on like their own linker and compiler for x86, but they probably use Clang a lot. All right, chapter 12. There. All right, let's see here. We got it installed. Next step. I just want like a basic help. Oh, here it is, hello world. But they don't have you type it out. What? Zig and net. Main Zig. I don't want all this build stuff though. I think that's where Rust kind of like went wrong, is like forcing all this stuff on you. Like Go, you just create a Go file and then you go run it. It's like the most basic thing. Is there a Zig run? Let's just write this out. Okay. So maybe in here we do a main. Oh, I should probably run Vim and do that. What's it called? Lazy extra, and then look for a Zig. Yeah, install that. Not, what, X, I think it is? Yeah. Zig. Cool, cool, cool. So quit out of that. That'll install a bunch of stuff, right? So now main. Bam, look at that. Look at my main. Prints. Hello world. Something like that. I think it's at import. Maybe like that. All right. Look at that. Look how beautiful that is. Ah, Rust, take notice. Why would anyone use Rust? I guess it has the safety guarantees, but like, it's just such a heavyweight thing to set up with cargo and everything, and it forces a specific like way of doing things. And there's a separation between Rust C and cargo, and it's kind of like a little bit insane. All right. So in here, I want to make a syscall. So I can say const Linux is equal to standard.os.linux. And then in here, I can say, hey, I want a var called UTS. I don't think it's called UTS. Like man up uname. It's called buff. But the struct is called UTS name. So we'll call it buff. And you give it the type. Can I just, yeah, linux.uts name. So imagine that 0 initializes things. Can do 0 like that. But I can't do that. Okay. And then here I'm going to say, hey, Linux dot uname, give it a reference to buff, gives me back the const rc. It's not called rc, it's called return. If rc is less than 0, say not equal to 0, why not? I like doing less than 0. Less than 0, then turn. What is this error thing? Error.uname failed? What is that? Since we have standard, we can just say standard dot print. We can't just say print here. Print standard debug print. Sysname. Is it println? I need println here. Here I'm gonna say, hey, uname output, and then I'm gonna go under this thing here, grab all these, paste them here so I know what they are. So it's gonna be node name, release, version, machine, domain name. Oh, and I need to put the format specifiers here, which I guess is like that, like a Python type thing. Oops. Is it O or S? 0, alright. And I guess I don't need to return here. So, okay. Let's go ahead and run it. Okay, it doesn't like the 0, so that's say undefined. Too few arguments to what? Extern struct declared here. Too few arguments on the right side of things. If I just comment out these prints. Oh, because I didn't provide the arguments here. Just needs to be like what? Buff dot sysname. Is that how I do it? I'm gonna comment out these for now. See if that works. Yeah, and then I need the new lines. New line, oops. New line. New line, please. Alright, I gotta get the fuck out of the way here. It's messing up my typing. New line. Okay, yeah. And this will be buff dot something. This will be node name, release, version, machine, domain name. Bam. Cool, cool, cool. And I guess I could do it all as like one, right? With these things, can I do like instead of dot and all that stuff, can I just pass it in like this? Buff sysname? No. Because args is a struct. Print takes in, it's not a variadic thing. It's literally like, give me the args of any type, but it's not variadic. Does Zig support variadic as I spell it? Arguments. Variadic. Yeah. Okay. Do I even need to provide the args though if there's nothing there. Is that safe? No, it doesn't like that. Alright. Yay, my first Zig program. Do you wish... no. Make file. I need to update this to now. Grab. Zig. Let's be under, not under ref or build ref. Zig program binaries here. Zig. Zig. And then if I say echo, I need to add these here. I usually just call this thing test and give it echo. So the dollar like this. Zig. Sig. These will be like this. Percent. Zig. Doesn't need the library options. Okay. Zig build. Outputs. Yeah. How do I compile a single .zig file and link it against precompiled .o files and header files? Okay. Build exe, it's called. Zig build exe. What is LC? translate C. Well, that's for libc. I think LC is for libc. Okay. And then this will be zig, like that. Disambiguate them. Make did not pick up on the zig file. Did I not write this? Oh, these need to get yeah. Pass up to that to underscore zig like that. And then we'll test this thing again. Oops, echo. Make test. Yep. I was doing a dash O. Maybe it has to be at the end instead of there, like that. Oh, I need to put the dash I after. Okay. Happy to do that. Nope. Still doesn't like that. ChatGPT is just making shit up. Okay. So maybe I'm gonna delete this. I'm gonna go up here and delete this as well. And I'm gonna move uname.zig to uname.zig. And then here, I'm set at GCC, I'm gonna use zig cc. Then I can just use all the same flags. Make clean, make. And here, I'll do zig as well. Look at that. Cool. And then I'm just going to open this up and say can you unify these make target? ChatGPT just lies half the time, man. Alright. I'm done having fun here. Let's go back over to here. We're almost done with this chapter, so let's just get through this. So system identification uname returns a range of identifying information about the host system in which the application is running in the structure pointed to by UTS buff. The UTS buff argument is a pointer to UTS name structure, which is defined as follows. Sus v3 specifies uname, but leaves the lengths of the various fields of UTS name structure undefined, requiring only that strings be terminated by null byte. On Linux, these fields are each 65 bytes long, including space for a terminating null byte. On some Unix implementations, these fields are shorter. On others, e.g. Solaris, they range up to 257 bytes. The sysname, release version, and machine fields of the UTS name structure are automatically set by the kernel. On Linux, 3 files in the directory procsys kernel provide access to let's cat that out. Cat out procsys kernel. Oops. sysname. Proxys kernel provide access to the information and is returned in the sysname release version fields of these read-only files are respectively OS type, OS release, and version. OS type, OS release, and version, which matches up to sysname, release, and version. Okay. Another file, proc version, includes the same information as in these files and also includes information about the kernel compilation step. Cat proc version. Okay. I.e. the name of the user that performed the compilation, the name of the host on which the compilation was performed, and the GCC version used. Alright. The node name field returns the value that was set using the set hostname system call. See the manual page for details on the system call. Often this name is something like the hostname prefix from the system's DNS domain name. The domain name field returns the value that was set using the set domain name system call. See manual pages for the definition of the system call. This is the network information service NIS domain name of the host, which is not the same thing as the host DNS domain name. Okay, great. The get hostname system call, which is the converse to set hostname, retrieves the system hostname. The system hostname is also viewable and settable using the hostname command and the Linux specific proxys kernel hostname file. Proxys kernel hostname. Hostname. Sorry, dash F. Okay. The get domain name system call, which is the converse to set domain name, retrieves the NIS domain name. The NIS domain name is also viewable and settable using the domain name command and the Linux specific proxys kernel domain name file. Okay. So it's proxys kernel domain name, none. The set hostname and set domain name system calls are rarely used in application programs. Only the hostname and NIS domain name are established at boot time by startup scripts. I'm going to ask the AI, I'm going to say, hey, what is the difference between the NIS domain name of a Linux machine versus the DNS name? Yeah. Network information service is a legacy system for centralized configuration of information like users, groups, hosts across a set of machines. Not related to DNS, just logical name used to identify an NS namespace. YP domain name? What is that? YP domain name? That's not a thing. Etsy default domain? What is that? That's not a thing. Alright. So then we got have this program here, which basically goes in and does all those things. Cool. Summary. The proc file system exposes a range of kernel information to application programs. Each proc PID subdirectory contains files and subdirectories that provide information about the process whose ID matches PID. Various other files in the directory and directories under proc expose system-wide information that programs can read and in some cases modify. The uname system call allows us to discover Unix implementation and the type of machine on which the application is running. Further information about the proc file system can be found in the proc manual page, kernel source, file documentation, file system proc, and various files and documentation sysctl directory. Exercise. Write a program that lists the process ID. Okay. What we got going on here? Alright. Make clean here. Write a program that lists the process ID and command name for all processes being run by the user named in the program's command line argument. You may find the user ID from name function from listing 8.1 on page 159 useful. This can be done by inspecting the name and UID lines. Okay. CPU name zig to exercise 12-1.zig. I might replace this with an underscore. Fine. 5.6 exercise, 5.6. Okay. MV exercise. Oops. 12-1-exercise.zig. Here, of course, we can blow away all this stuff here. Give me the zig code to include a header file and call a function in that file called user ID from name. C import. I don't need this stuff anymore. Oops. This is going to be called the Linux programming interface header, something like that. I forget. Reflib HDR. And then in here, I can then say, hey, do I have my clang stuff going on here? Do I clang? Yeah, that should be able to find that. Then in here, I say, yeah, why don't we do that? C0. UGID functions.h. If I open up reflib, the Linux programming interface, okay, so that doesn't have those. So I have to include that myself, which would be UGID functions.h. Oops, UGID functions.h, like that. Okay. I'm in lazy vim neo vim, and the editor is complaining about not finding my header files. How do I give the the Zig compiler language server the location of my header files? .clang-d, I already have that. Compile flags add. Let's try that. Vim build.zig. Oops. Let's try it. Okay, I can find it without that. It just was having a bit of a hard time initially. All right, so it says write a program list the process ID. So list the PID. What else we got going here? Command name. For all processes. Okay. Resolve username to UID. Find all processes for all processes. PID and command name. So here we go. This could be equal to how do I get the first arg a Zig main program? So yeah, we gotta validate that. Say if args.len is greater than 1, then we can do our thing. If it's less than or equal to 1, then we need to say, hey, or you say less than 2, right? Print usage. And then I'll test the for declaration thing. Print, fn print usage, and we're just gonna say print usage. It's gonna take in const char star. This would be arg command, and then this will be command here. This will be, oops. S, and then this will be required username, and then I need a new line, and I need to return or exit os.exit. Standard OS. this needs to be a array of const u8 like that. Maybe we did something like const foo is equal to args sub 0. So that gives us back this thing, which is some type of array of u8. Why does it say expected after parameter? Oh, maybe I got this mixed up. Is it like this? Oh, really? I didn't realize that. And then it doesn't like that, so maybe like that. Write me a print usage function that takes the first arg and interpolates it to a string. Oh, you have to have the K. So used to go and then void here. Alright, there we go. Has no member exit. Last time I did this, it was like a lowercase error. Yeah. So now it's freaking out again for that header file not being there. So what we'll do is go back up here, grab that build thing, build.zig, paste it, oops, paste it in there, and null.zig. There we go. Don't care about that. Now when I go back into here, we'll be able to find it. Yeah, it looks like it. So we need that. This make file filter out build.zig. Okay, make file, just gonna do a test here. Test. Oops. Echo out that. Make test. Oops. Make test. It's gonna be trying to build the build thing. So replace that with this. And see if that works. Looks like it. So now we can delete all that. Go back over to here. Make. Looks like everything worked. Great. Oops. Okay. Okay. This can be done by inspecting name UID lines of all the procpid status files on the system. Walking through all the procpid directories on the system requires the use of readdir, which is described in section 18.8. Make sure your program correctly handles the possibility that a procpid directory disappears when between the time that the program determines that the directory exists and the time that it tries to open the corresponding procpid status. Readdir. entry name. I think differs in Zig are block scoped. Yeah, they're block scoped, whereas in Go they're function scoped. All right. Hopefully that fixes the issue here. It's this guy here. No. So you call next, say while lines iterator dot next. So BA lines typo. Self. Where's that at? Expected type mem, pointer to mem split iterator, U8. Okay. Oh, I'd say var. That's probably it. Var lines generator standard memory split any U8, the contents, the delimiter, and then lines iterator next line. That looks correct to me. Okay. Okay. File. Clearly this is a binary of some sort. Build. What do you name Zig? It's okay, it's an elf binary. So why can't I make clean, make clean, make? Okay, now we're back to this. Error expected 3 arguments, found 2. Comp time type. So I think this type needs to be U8 like that. What the hell is going on here? Oh, there's 2 of these. U8 here. Trim also needs it. U8. Split. This is going to be another split any. This will be a U8. Parts iterator, which is already a parts here. Try parts next, or else continue. Okay. We'll just call parts next. Or else continue. Oh, yeah. Okay. That fixes that. Hey, look at that. Fuck, man. Build exercise 12. Okay. C0. I could do this in C a lot faster because I don't know Zig. Is that try next? IT next? $32. There we go. Make clean, and then make this, and then build 12 there. Comparison with null. Interesting. Okay, so we can just delete that. Okay. Gotta panic. 32. Why does it panic? I understand it can error out. Why do we do while true? Why don't we do while IT next here? While entry is equal to IT next. Shouldn't that be the way that we do this? And then maybe colon equals here? No. Var entry? Oh, we do while IT next. How about we grab this thing, code rename, call it dir IT, or actually code rename dir iterator. There we go. And then this thing, this while, we say, hey, in here we're gonna have a entry like that. Try catch or if. In Zig, how do you iterate over a directory listing? Try. There's a try there. Okay. Try. And the panic is on 24. Iterate true. Okay. Dot iterate is equal to true. Seems rather verbose. Okay, now we're getting further. Invalid character. Oh. So we got FB, all this stuff. We're like, okay. And we got the one, it's like invalid character. This is under 52 here. Oh, because we actually got to parse it. U32. Why is it freaking out about that? Oh. This is a different one. So I'm going to print that out under here. We're going to say, hey, you're going to be the real user ID stir. That doesn't make any sense. Buffer length is equal to 0. Oh, I forgot to replace this here with real UID stir. Yeah, it's empty. Something wrong there. Okay, I'm gonna print out the whole status content here. Okay. So we got our one status content, and then we split on new line. Great. We're iterating over those things. UID here. Oh, because there's like spaces and shit before it's 0. So we say, hey, if you start with UID, then I'm going to split you up. And start at 4. 1, 2, 3, 4. Which would be a bunch of empty space. And delimiter is a /t. Are those /t? It doesn't look like /t to me. Let's wlan paste them into odd xa. Okay. Horizontal tab, yeah, those are tabs. So you have delimiter tabs. So I think I need to go 5 here. And that will drop that tab. And then we get the next, or else we continue. Okay. And I'm going to delete this thing for now because I think I'm good on that. Bam. Wait a minute, only UID? What is that? That is not the only UID for 0. If I do UID, it's 1000. So why does it come back as this crazy number? Is this like a C? It's probably passing this into theirs, coming back with the wrong thing. So let's go into the UGID function C, and this is going to be arg0. I'm going to say print that thing out. That's going to be a string. So we'll say args of 0 is equal to string that. And then in here, this will be the user ID from name. We're going to say printf %s new line. Oops. And then here, we're going to say name. And we're going to say, hey, this is going to be the name. Make. Oh, because I passed in 0 instead of 1. That makes sense. Hey, look at all that stuff. It worked. So I got my OUID there. Yep. Here, I can now back out of that. If I do like Docker, there's nothing there. Cat Etsy groups or password. And then here I do like, hey, what's the QEMU user up to? And I can DT that. Oops. There we go. There we go. And here, I could do something like maybe cluster. Nothing around there. System D. There should be a system D. Network. Okay, it's got its process running. Maybe a time sync. What about a system D? What about mail? Is mail running? Anything? Mail? Or FTP? Shouldn't be. Let's see what system DOM is doing. Ain't doing nothing. What else? Git. Alright, seems to work. Let's review it. Write a program that lists the process ID and command names. I need both. So let me open up this again. So I need issue the PID and command. And the PID is going to be UID, not UID. This would be, where's this? PIDster. Which would be a string. It's the process ID and command name for all processes being run by the user named in the program's command line argument. You may use the this can be done by inspecting the name and UID field lines of the proc PID status. So here's our name and UID. Walking through all the proc PID directories on the system requires the user reader. Does it? If I do strace s that, sorry, C, right? Yeah. Is there a reader going on here? I don't see a reader. Oh, reader is not a system call. Man 3 reader. Okay, that makes sense. Alright, use the reader, which is described in section 18.8. Make sure your program correctly handles the possibility that proc PID directory disappears. Alright, boom, boom, boom. Write a program that draws a tree showing the hierarchical parent-child relationship of all processes on the system, going all the way back to init. For each process, the program should display the process ID and the command being executed. The output of the program should be similar to that produced by pstree. Although it does not need to be sophisticated, the parent of each process on the system can be found by inspecting the ppid line of all the proc PID status files on the system. Be careful to handle the possibility that the process parent and thus its proc PID directory disappears during the scan of all proc PID directories. Huh. I'll be back. I gotta take a little bit of a break, but this should be an interesting thing to solve. Let's see here. Yeah. All right. It has been about 3 hours that I've been streaming, so I'm gonna go ahead and take a break for lunch. And we got these two exercises that I'll resume when I get back. This one, just painting a tree of all the processes. There's like a billion ways you can skin this cat. Again, I want to use Zig just because I'm trying to get a little bit more familiar with it. My initial thought with this was to use I think they call it like an association table to show the tree. So we know how many PIDs can exist, maximum PIDs that can exist on a given given machine. We can actually dynamically discover that, but it's like something like 65,000, something like that. Cat proc PID max kernel sys PID kernel PID max, yeah. So that's about 4 million integers. So I was thinking about creating like a 4 million array, and the value of each, the integer value of each element of the array would be its parent. So you would allocate basically 4 million. Well, it'd have to be something that could contain up to 4 million in value. So Python -c, we'll just do like print 2 to the power of 10 would be 1024, 18, 20. 20 is a million, so maybe 24. If we're going by 8, it'd be 8, 16, 22. Yeah, so 22 would be, wait a minute, 24. So 22 bytes. So we would have 24 bytes, or 24 bits, which would be 3 bytes. So each element, so it'd be 3 times this value here, 3 times 2 to the 22. 3 times 2 to the 22, and I think that evaluated correctly. No, did not. Did it? Yeah, it did. The precedence was right there. So it'd be 12 megs of memory. We just allocate that up front. We can probably put it on the stack, maybe. I don't know. But basically we need to allocate that up front. That's going to be our array, association array, the value of which is the parent PID for that index. If the index is not a valid PID, then we just put null for the parent. And there is no null PID, because everything goes up to PID 1. Null PID is like the kernel or an error value, sentinel value, so we can use that. So that's to represent all of the data. So we just like get all of that from the proc file system. Like for every PID, we just populate everything. It seems wasteful though, because we're gonna be iterating. It's constant time, so that's not like, algorithmically it's not complex, but it seems wasteful to have to iterate over to like, you know, what is it, 4 million different values if there's only like 3 processes running. So the other thing would be some type of like hash map, like an ordered hash map. I think there's like an array list in Zig that I heard about. Let's see, array list. No, not Java. Zig. that's kind of like a ordered okay, it's like a vector. That's the other thing we do is just like a vector, and we can have elements in the vector, so it'd be a little more memory efficient. We could probably pre-allocate the max number if we wanted to. Just have space. So it's a table double. The thing is that we really want to start at PID 1 and then traverse down all of its children when we're printing out. Just print out PID 1 and then we go to its children, print them out, or print his first children out, print that's first child out, and then recurse. So it's a depth first algorithm for printing. And we want to go through its children, not through parents. So really what we want is a hash map that maps a PID to its children. And then we iterate over every single PID in the system. We get its parent PID and then we add it to its children's array list. And then we can print it out. I think that's what we'll end up doing. So that's not too difficult. Write a program that lists all processes that have a particular file path name open. This can be achieved by inspecting the contents of all the proc PID FD symbolic links. This will require nested loops employing reader to scan all proc PID directories and then the contents of all proc PID FD entries within each proc PID directory to read the contents of proc PID FD, and symbolic link requires the use of read link. All right. So we'll do those when we get back from lunch, and then the next section is on file IO buffering. Which takes us to 250. $250 is about 1/6 of the way into this book. Then we arrive at file systems. Okay. Cool. I'm gonna go get lunch. I'll be back in probably a couple hours, just because I need to relax a little bit. I don't have any food in the house, so I have to go to the grocery store too. So yeah, I'll be back.